In the back, can you hear me? Can you hear me? Okay, great. So remind me if you cannot hear me anytime during the class. I post a link, a playlist of our recorded lecture. So I'll make sure to do that for all the rest classes this semester. So it is okay if you are busy sometime that you cannot come to this class. You just make sure that you watch the recorded video. Do not wait until the night before exam and watch that. If in that situation, I recommend not watch it at all. So and also you need to know that for the attendance, well, we'll start doing attendance start from Friday because today is just the drop and add deadline. And if there's something that make you unable to come, there's no way I can give the attendance. No matter whatever reason it is, it's like you have the doctor note, you have the UF activity, you are athlete, you are have military service, anything. Those will be including the 3 drops. So I only give attendance if you are here. So let's continue with last time. So we talked about the inverse of the matrix and the inverse for hand calculation. I only require to do 2 by 2. Anything higher than 2 by 2, you can use MATLAB. And of course, for real life situation, you use Abacus. And this is what Abacus is doing, like behind the whole thing. So for the inverse matrix, if the determinant is 0, inverse does not exist. And if we define this B matrix is the inverse of A, and then this A matrix times the B matrix becomes the identity matrix. Or we can write it as it's also equal to B times A matrix and equal to identity matrix. And of course, this function as 1 in the scalar operation. It's more like 2 times 1/2 equal to 1. But in the matrix operation, there's really no 1. The identity matrix is same function at 1. So this is the determinant inverse. What else? Diagonal matrix, identity matrix. I already the homework 1. For that one, I don't think it's anything like really crazy. You need to use MATLAB. Make sure that you do hand calculation. Do not use MATLAB for homework 1. For the later homework, if after boundary condition goes higher than 3 by 3, you can use MATLAB. But for homework 1, it's purely ask you to practice if you truly understand these basic concepts. You can use calculator, but do not use MATLAB. And the next one is eigenvalues. So basically, let's say we have a matrix A times a unknown vector we need to calculate equal to lambda times this vector. So this is definition of the eigenvalue. But of course, this is pure math. We know that we learned about the eigenvalues in solid mechanics when we find the principal stresses from the state stress matrix, right? So we have the 6 independent components, all the sigma, all the tau. And then for finding the principal stress, the 3 principal stresses, it's basically the eigenvalues of the 3 by 3 matrix. So, so for finding this lambda eigenvalue here, let's put the definition here. The lambda is a scalar and it's the eigenvalue of the matrix. The eigenvalue is also very important for the balcony analysis we will talk about later. It's not only for the principal stresses. So for finding the eigenvalue of this A matrix, of course, let's say we move this to one side, then it becomes x minus lambda x equal to 0 vector. And again, lambda is a scalar. We cannot really say that A matrix minus lambda times vector x, right? So what we need to do is that convert this lambda to a same dimension matrix. So of course, just imagine that in the scalar operation, multiply by 1. And here in the matrix operation, we multiply by a identity matrix in the same dimension. So for this calculation, we can write as A matrix minus lambda times identity matrix. Identity matrix dimension is same as A matrix. And now we have the X vector equal to 0 vector. And now you can see here, a matrix times a vector equal to 0 vector. And we know that, well, normally, let's say for FEA, it's the K matrix for your structure. This is the degree of freedom. And this is 0 vector. So normally, this one cannot be 0. So if you want this two product become 0, we need to make sure that this one equal to 0. And when we say the equal to 0, it's the determinant of this matrix equal to 0. So this is how we solve the eigenvalue problem. So the determinant of A minus lambda I should be equal to 0 to make this become the product of these two become a 0 vector. So for finding the lambda determinant of this one equal to 0, I can simply write this one as, in general situation, let's consider a square matrix with n row and n columns. So it's basically 1, 1, 1, 2. In the first row, I have 1, n. And the same thing, 2, 1, n, 1, a, n, n. And this minus lambda times identity matrix. Identity matrix, it means that all the diagonal terms, they are 1. All the off diagonal terms, they are 0. So minus this lambda times I is basically a 2, 2. And this one also. So we need to make sure that this one is equal to 0. And if it's 2 by 2 and 3 by 3, of course, hand calculation, we already show how to calculate determinant, right? So I do expect you to know how to calculate the eigenvalue of 2 by 2 and 3 by 3 in exam. In your homework, anything higher than 3 by 3, MATLAB. So for how to find, I mean, if it gets more complicated, how to use the MATLAB, you can simply define the A matrix and then use the EIG A. Then they will return the eigenvalues. So if it's n by n matrix, we should have n eigenvalues. For hand calculation, let's do a simple example here to show you guys. Let's say if we have a 3 by 3 matrix, the A matrix I put as 1, 1, 4, 0, 2, 0. I put many 0 components here to simplify our calculation. But even if it's non-zero, we still can do it by hand calculation. So to find, let's say this is a 3 by 3 matrix. To find the eigenvalues of the 3 by 3 matrix, we need to make sure that the A minus lambda times I, we need to write this one and make a determinant equal 0 and calculate determinant and solve for the I. So it becomes 1 minus lambda. And this diagonal term, same thing. And all the off diagonal term, since identity matrix off diagonal term are 0, so this maintain the same. And we need to make this determinant equal to 0. So back to our definition, how to calculate determinant. This is the equation, and of course, this equation will be provided in the exam. So specifically for our example, I can write as the first term and 4. So it should be this one times this one times this one minus 0 times 0. All right. And the second term well, this is 0 here, so there's no second term. And third term is this one, and 0 times 0 minus this one times this one. So I put the negative sign here. 2, 1 minus lambda equal to 0. So I simplify this equation, it becomes and of course the 3 eigenvalues, they are 1, 5. So this is just simple example. I'm pretty sure you did this one before in other class. Let's say these are the 3 normal stress sigma x, sigma y, sigma zz, and this is the tau xz. And then you calculate principal stress, and you calculate 3 eigenvalues, and principal stress normally put it as the maximum one as the sigma 1. So this becomes sigma 1, sigma 2, sigma 3, right? It's the same thing. Any question? So now the next topic is, and of course, it's not just principal stress. We'll see later that eigenvalue is very important for buckling analysis. We talk about it in detail later. The next one is the matrix operation. So for addition and subtraction, that one is simple. You just have the corresponding component, add them or subtract them. So this one is say if we have a C matrix, of course it should be the same dimension A and B. Plus minus B matrix. Then it's simply the corresponding component in the C matrix should be equal to A ij plus or minus B I j. And of course, let's put it here, A and B should be the same dimension. Otherwise, you cannot do the matrix addition and subtraction. For the matrix multiplication, it does not really need to be the same dimension. It's just the second index of the first matrix and the first index of second matrix should be the same. Then we can do the operation, right? So for the matrix multiplication, let's say if A is n by k and B matrix, the first index should be the same as the second index of the first matrix. So it should be, let's say, k by L. And n and L can be really anything. So the new matrix, the dimension should be n by L. And for the new component Cij, in the C matrix, it should be the sum of the k from 1 to k and A, B, K, J. Well, let's use a simple example to show you guys quickly understand what it means. So let's say I have a 1 by 2. Use simple situation. And let's say the next one we have 2 rows, 2 by 3. Can anybody quickly tell me what is the result of these two? The component of the 3 components. Yes, thank you. So basically, this one means the first component here is 1 times 3 plus 2 times 0, right? Second component equal to 1 times 0 plus 2 times 4. And the third component is 1 times 5 plus 2 times 0. That's how we get, of course, this is, you can say this is a row vector, but I mean, vector is a special case of the matrix. So just want to simplify the example here to save some class time. Any question here? Okay, so now this is the matrix operation, multiplication, and there are some rules of the matrix multiplication, because it's not simply like in the scalar operation, you can just switch the position and inverse transpose everything. There are some rules you need to be careful when you're trying to switch them. Sometimes it doesn't work, because simply, let's say, if you want to make sure these two dimensions are the same, so you cannot simply say that A times B equal to B times A. Rules of the matrix multiplication. So the first one is associate rule. Basically, if we have three matrices, we can calculate the multiplication of the first two and then times C matrix, or we can use A. We calculate multiplication of the B and C matrix and then A. That A should be on this side. So this is the associate rule. The second one is the distributive rule. So if A matrix times B matrix plus C matrix, and of course B and C should be the same dimension, so we can do A times B matrix, multiplication of A and B matrix, and plus A and C. Sorry, should be A and C. Multiplication of A matrix and C matrix. So this is a distributive rule. And third one is the one I just mentioned. So A times B is not equal to B times A. It's a different thing. Non-commutative. Next one is a transpose product. So let's say if you have the A, B, the multiplication of A and B matrix and transpose, it's not A transpose times B transpose. You should switch the order. For the detailed derivation, we can talk in the office hour, but I don't think it's necessary. It takes a lot of time to prove that, but I don't think it's necessary here either. This is not a math class. So same thing for the multiplication of three matrix. So what you need to do is that C transpose times B transpose times A transpose. And this is very similar for the inverse. So let's say if we have the multiplication of A and B and we calculate inverse, what we can do is that we calculate B inverse and then times A inverse. Same thing if we have a three matrix. Then it becomes C inverse, B inverse, and A inverse. So those are two rules for transpose of the product and the inverse of the product. Now let's talk about the matrix equation solution. It's something you need to use for every problem. I mean, in the exam, I will not really ask you like the pure based on this, like character inverse, character determinant matrix. I give a matrix character determinant. That's not the goal about FEA. But our exam is purely based on the FEA. But for every problem, let's say you have the matrix equation, you assemble them, you apply boundary condition. In the end, you need to solve them. So for that part, you do need this content. And if you cannot do that, there's some penalty. So. But there's no separate question like specifically for the mathematical preliminaries. Matrix equation and solutions. Let's assume that we have n matrix equation. And for each equation, let's put in this way. Well, let's put in matrix form directly. We have a n by n matrix, 1, 1, 1, 2, 1, n. Second row, 2, 1, 2, 2, 2, n. The last row we can put as n1, a, n2. And this one becomes n. So let's say we have a vector, something we need to solve. Or in FEA, it's a degree of freedom, displacement or rotation or anything. x1, x2, xn. And equal to another vector, which in FEA could be the force in general term. So force in 3 dimension and the rotation and the moment in 3 dimension, about 3 dimension. Let's put as B1, B2, Bn. And of course, if we define the matrix as the A matrix and vector as the unknown vector x we need to solve, and the right hand side becomes the B vector. How to solve this one? How to solve the x vector? A inverse, right? You move the A to the right side. But of course, you cannot simply say that, okay, it's B vector divided by A matrix. No, it's A inverse times B vector. So another question is that if we have the x component here, unknown, n component, sorry, n component in this x vector, they are unknown. And if we have this n by n matrix and we have given this vector, that means that we can definitely solve for this x vector? Yes or no? If we have the n by n matrix here, given information, we have the a vector with n vector here, does mean that we definitely can solve this n unknown. Why no? Thank you. So this matrix could be singular. If it's singular, the determinant is 0. So there's no inverse. Back here, right? There's a chance that the A matrix could be singular and the determinant is 0. So there's no inverse and you cannot really solve A inverse times B. Actually, for FEA, all the matrix after all the element matrix stimulated for element, and after assembly, all of them, they are singular matrix. And we need to do something to remove the singularities to solve it. We'll talk about it later, but you need to know that for this matrix equation, when you see some matrix operation like this, equation like this, it doesn't mean that we can always solve for this one. The only way we can solve this one is that this one is not singular. So now let's assume that A is not singular, then we can consider then basically let's write in detail. We put A inverse on both sides equal to A inverse times B. So, and of course, A inverse times A equal to identity matrix. Identity matrix times X equal to X, right? So this is how we solve this unknown vector X. So it should be equal to A inverse times B. Let's do a very simple example. A matrix equation, a matrix times a unknown vector xy is the unknown component in this vector, and let's say this vector is given information. So we need to solve for x and y. And of course, I know that some of you just see this equation and say, okay, 7x 3y equal to 12 and 3x 3y equal to 24. So basically, if I use the first equation minus the second equation, you have the 4x equal to negative 12 and x equal to negative 3. You solve that using the method in elementary school. Yeah. So this is not the point here. I just want to I just use this simple example to show you how do we do this, and you will understand that how the abacus actually solve a big matrix. Let's say if you have 1,000 nodes, I talked about in the last class, you may have 6,000 by 6,000. So you need to know how abacus is actually doing. So this one, let's say we need to solve for the vector x, y. So what we need to do is that we take the inverse of this matrix times this given vector. And inverse of this matrix for 2 by 2, determinant 21 minus 9. And for this 2 by 2, the diagonal term, we need to switch the position. So now this becomes 3 and 7. That all the diagonal term we need to add negative sign. Negative 3, negative 3. And this vector 12, 24. So now for negative 3, 11. So basically, of course, you get the same answer, x equals negative 3, y equal to 11. So basically, you have this coefficient, this one times this one, this plus this one times this one. This becomes a negative 3. And the second component, y, is this one. So this is a common coefficient, and negative 3 times 12 plus 7 times 24, and you get 11. So this is how we calculate the unknown vector. If we have matrix times the vector equal to a given Mason vector. So we need to use the inverse of the matrix. Any question? Do you guys hear about like the positive definite, positive, negative definite, positive semi-definite, those kind of thing for the matrix equation, quadratic form? Yes? Okay. I probably will talk about that later. So for that part, when we actually need to use it, I will talk about that. Let's skip it for now. I think for majority of the FEA problem, this should be enough. Let's now start some real FEA stuff. We start with the simplest element type is a spring element. Spring element is simplest because it can only move in one direction, right? Let's say you have a spring, you cannot apply a force like this. You can only apply a force in the spring x direction. It can be either tensile or compressive. So for each node, there's only 1 degree of freedom, and the force can only apply it in the x direction. So this is in the textbook 1.1, direct method for spring element. Not our definition from a single element. Let's assume that in general situation, we have one spring element. It's ugly, but it's fine. So let's assume that this is I node. Let's use different color. Well, it's fine. This is I node. This is J node. And of course, if you have a big system with 100 springs, you may have different node order. So let's say for a single element, I have node I and node J. And for the force applied at node I put it as force at node I. For this specific element, I put it as E. And the same thing for the force applied at node J, I put it as J. So this is node label. And the superscript becomes the element label. It's the same here. I means node I. E means this specific element, spring element. I just want to make it consistent with textbook, so you guys don't get confused when you read textbook. And we define the K of this element as the stiffness of this spring element. So and also we have the force, we have the K displacement. Let's say at node I, we have displacement UI. Since it can only move in the x direction, and we normally, if there's only one direction, we assume it's the x direction. So we use the U as displacement in the x direction. This is the UI. And at node J, we have displacement UJ. And of course, if coordinate is, we always assume this is the x-axis. Now let's try to use this as example of how to find the K matrix for this one, how to write the element matrix equation for this single spring element. So for the elongation of this spring element, delta of the element E is simply uj minus ui. This becomes the elongation of the spring element, right? And for the element force, I'm pretty sure you guys learned from previous class, equal to the stiffness times this elongation. Let's put P as element force, and superscript E means for this element equal to the K stiffness of this element times elongation of this element. So it equal to K uj minus ui. So to make a connection from what you learned from the mechanics materials, this element force here is the same as the internal force. When I say that it's same as internal force, it means that it has a sign convention. When it's tension, it should be positive. When it's compression, this P should be negative. So this sign convention is the same no matter it's in the mechanics materials or your other solid mechanics like if this class or any aerostructure Mech 1 should be the same. So this is a sign convention for the element force. So based on this sign convention, let's put it this way. When uj is greater than ui, so the displacement in the second node is greater than displacement in the first node, it basically means there's a elongation, or this one is positive. So element force is positive, it's tension. The element force PE here should be positive, and it means tension for this one. And for the nodal force, how to generate a nodal force to create this tension situation? Let's say this I and J. If you want to have tension in a spring element, it means that, let's say this is node J, this is node I. It means that my force applied at node J should be in the positive x direction, and my force applied at node I should be in the negative x direction. In this situation, we can generate a tension in the spring. Make sense or not? So again, if somehow you forgot about the sign convention for the external force and internal force, all the signs for the externally applied force. So this is the force applied to node I, and the force applied to the node J. So it's the externally applied force to this spring element. The sign for the external applied force is always following coordinates. So if it's applied in the positive x direction, it should be positive. It's applied in the negative x direction, it should be negative. But the sign convention for internal force, don't get confused. P here is the internal force. It's always, whenever it's tension, the internal force of this element should be positive. Whenever I apply compression, the internal force should be negative. So this is a sign convention for external applied force and internal force. Don't get confused. So now let's say to generate tension, the force applied at node I should be in the negative x direction, and the force applied at node J, it should be in the positive direction to generate this tensile force. And of course, there's another situation. When uj is smaller than ui, it means compression, right? So back to the equation. If uj is smaller than ui, this one becomes negative. So it is compression. And how do you generate a compression in a spring element? So basically, now the force applied at node J should be in this direction, and force applied at node I should be, right? So basically, it means that force applied at node I should be in the positive x direction, and force applied at node J should be the negative x direction to generate this compression in the spring element. Make sense? Okay. Now we put positive and negative. So now we can try to find out the matrix equation for this spring element. We write this one in a way that Fi equal to K Ui minus Uj, and Fj equal to K negative Ui plus Uj. So basically, you can see here, we already have P equal to K Uj minus Ui. But based on discussion about sign convention and sign convention for the internal force and sign convention for the external applied force, we know that it's always the same of the internal force and the external applied force and node J. So the Fj should be equal to PE, should be equal to K Uj minus Ui, right? And for force applied at I is always negative of PE. So now it becomes Ui minus Uj. And of course, magnitude should always be the same. No matter it's in statics, mechanics materials, aerospace structure, FEA, Mach 1, anything, our structure stays in equilibrium, which means the magnitude of Fi and Fj is always the same to maintain our spring element in equilibrium. The acceleration should be 0. So now this is the two equation. Of course, in FEA, we always put it into a matrix equation. Now it becomes, we have a matrix times Ui, Uj equal to force vector, which is Fi of element E, Fj of element E. What are the 4 components in this 2x2 matrix? I just simply write these 2 equations into the matrix form. So K Ui minus K Uj equal to Fi. So K is a common coefficient. I put it here. So I could put it in this way, right? So it's the same thing. K times Ui minus K times Uj. Oh. Why? Do you guys have Wi-Fi here? Okay. I haven't tried it for a long time. I was hired during COVID, so I never really writing on board before. I was using my iPad all the time. So let's do this. So for the two equation we put in matrix form is simply K. The first equation you can check correction out. The first equation is K times UI minus K times UJ equal to force and node I, right? The second equation is K negative UI plus K UJ equal to the FJ. So should be the same. I just write different form. And now this is the first matrix equation we learned in our FA class. This is the matrix equation for spring element. And now if you check this matrix equation, you can understand why I said before that all our matrix equation, they are singular. What's the determinant of this one? 1 times 1 minus next, it's 0. We cannot solve it. Anybody know like why it's always like this? What does it mean? Like the physical meaning, this is pure math. The determinant is equal to 0, and we cannot solve for the U and UJ. Why is that? What's the physical meaning behind it? Constant what? Constant stiffness.
Staying still.
Staying still. Well, let's say I have spring element. Let's say I'm standing here and spring and the displacement as this is J node is 0.1 and this one is 0. This could be the one set of solution. And now I have same force, I move here, and I can say that okay, I have the same tension, same force in this spring element, but displacement could be, let's say I move me 1 meter to the right. Now this one becomes 1.1 and this one becomes 1 displacement, right? I can move here. Now satisfy same thing, I generate same tension, the same elongation. Now this is 2.1, this is 0.1, this is 2. So the elongation I maintain as 0.1 and the force I maintain the same. So I can have infinite combination of U and UJ. What does it mean? In solid mechanics, what does it mean? Rigid body motion. Have you heard that one before? Rigid body motion. I have the same force applied to the spring element, but the spring element can move. So the elongation is the same, the force is the same, and but I have infinite combination of the U and UJ to make sure that UI minus UJ is the same. So this is the rigid body motion, and the way to make you have the infinite have a single vector UJ here to remove the singularity is I apply boundary condition. Let's say I fix this end. Now I only have one set of the solution, which is UI equal to 0, UJ equal to 0.1. We're done. Right. We need to apply boundary condition. I will talk about it in the next class.
Excuse me, sorry, this is my first class because I'm an international student. My flight kept getting delayed yesterday. I didn't pick up what you said on attendance. You said attendance is mandatory, right?
It's not mandatory, it's bonus.
Oh, okay.
It's bonus. So the syllabus on Canvas, I didn't put it there.
Okay.
So you can watch my first recording. For the health semester, I have 3 points in total, right? So, and if you come to all my classes, you will get 3 points in your final grade. And of course, I have 3 drops. So if let's say student activity, conference, anything, those are including the 3 drops. So it let's say if we have 35 class for the whole semester, you can get 3 points if you come to 32.
And that's starting now or starting now?
Next class, because today the drop I did.
Thank you.
Two. It's awesome. I don't know why. I feel so sad. It's okay. It's circumvention.